Okay, here we go. Welcome to our nice application problem. We're going to use the method of undetermined coefficients to solve a forced harmonic oscillator. In other words, a constant coefficient, non-homogeneous second order differential equation that is linear. And we're going to do that in an application of electric circuit theory. And again, disclaimer, I know very little about electric circuit theory, but we're going to use this problem from the book to get some practice. So again, the book would like to also call out that this does have realistic and rather messy numbers. So we're going to look at this resistor, inductor, capacitor circuit, or known as an RLC circuit, that's pictured right here. So suppose that the voltage at the source is given by this function, 2e to the negative t over 3. We looked at this a little bit, something very similar earlier on, but a simpler model. So this is the voltage that's coming from the source. If the source were 0, if there was no voltage, no source, then we would have a homogeneous and an unforced harmonic oscillator. But suppose that over time there is this decaying source of voltage, and it is decaying at an exponential rate, and we'll see how fast or slow that might be. But yeah, that's exactly what they say right here. Here's the resistor, here's the capacitor. We didn't actually look at the inductor, I believe, in chapter 1, but now we have the inductor as well. So a slightly more complicated circuit. So we're given some constants, and we have this model down here. You don't necessarily have to, you certainly don't have to have this model memorized. You don't have to know electrical engineering, but you should be able to use this information that they provide you with here. So R is some constant, which is 4,000 ohms. Tells you that omega stands for ohms. C is our constant. That's going to be 0.25 farads. And, microfarads, I believe. And F is going to be 0.25 times 10 to the negative 6 farads. And our constant L is going to be 1.6 henries, which I didn't even know was a unit. But yes, all of these are standard units in electric circuit theory. So the voltage across the capacitor is going to be a function. It's going to be related to our input source, and then things are going to happen. And we're curious about what is the voltage across the capacitor over time, and what we can say is that this situation, this system, this physical system, this electric system can be modeled by a second order differential equation. With all of these. And again, all of these coefficients are positive. They don't need to be positive, but they are all positive, which means that really this is quite similar to a forced harmonic oscillator. This is our kind of external force. External force in this case is going to be our source, our voltage source. So we need to solve this equation. You ready? Let's copy these constants down and solve. So to get started, you could plug everything in and simplify, or you could solve and keep these as parameters. It's kind of up to you. But to solve this, first we need to solve the homogeneous version. We need to solve LC times V double dot, again, the second derivative of V with respect to T. Kind of looks like a smiley face. Plus RC times our cyclops smiley face plus V is equal to 0. We're solving the homogeneous version first. And again, we can guess, and we know that our eigenvalues are going to be solutions to this quadratic function. These are our eigenvalues. We can use the quadratic formula to say our S is going to be negative B. All right, I'm going to write this down. This is A, this is B, and this is C. Surely I won't make any mistakes here. It's negative B plus or minus the square root of B squared minus 4 times A times C all over 2A. And you know what I'm going to do? I'm going to use a calculator to see what these numbers are. So we're going to go over to Desmos. And again, I really want to model. There's nothing new happening in this problem. It's just messier numbers. I'm trying to model kind of a good ways of approaching this sort of problem. So one such way that you can do is to go to Desmos. I'm just realizing I completely misread the problem. R is 4 kiloohms, which is 4,000 ohms. C is 0.25 microfarads. Still pretty sure this is micro, which is given in this many farads, and L is just 1.6 henries. So when we type these into, I'm going to use Desmos to store all of these so we can use the quadratic formula over here. So R is going to be 4,000 ohms. C is going to be 0.25 times 10 to the negative 6. And then L is 1.6 H henries. So quadratic formula says that our solution, or our eigenvalues, are going to be, what are they? Negative RC plus or minus the square root of RC squared minus 4 times A, which was LC, I believe, all over 2 LC. And it says undefined because it's an imaginary number. RC squared minus 4LC. Just making sure I typed it in right. I did not know Desmos. Complex mode. Yes, please. Thank you. Wonderful. So we get this lovely number over here. And we're going to approximate, and that's going to be okay. These are going to be the roots of it. And again, we know how complex roots work. If this is a minus, what do you think is going to happen? Yeah, it's the same thing. It just has, right? We have complex conjugates. So our roots, if we use a calculator, are going to be negative 1250 plus or minus, again, it's the square root of some number, but it approximates to about 968i. And again, math, we don't like to approximate, but in applications, you basically need to. Okay. If you wanted to keep this accurate, you could just call it some parameter. You could call it some parameter A or whatever. But for our purposes, this is going to work for us. Okay. So we have our eigenvalues. We know what our general solution is going to look like, right? Because we remember how to do this. And what we're going to find is that, well, we have complex eigenvalues, so we're going to need to use Euler's formula. So we could write this as a second order system. We know that one solution to our second order system, y of t, would be e to the lambda t times the associated eigenvector, which we could find. I'm going to skip over some of that, I think. And going to take us to our general solution. You could pause the video and work through that if you wanted to. And you're going to get that our solution is v of t. Our general solution is k1 e to the negative 1250 t times sine of 968 t plus k2 e to the negative 1250 t cosine of 968 t. Okay, a very nice general solution right here. And you can see a few things. That electricity is happening pretty fast, right? This is exponentially decaying so incredibly quickly, right? Negative 1250 T decaying so quickly. How fast is this oscillating? It's oscillating so fast. What's the period here? The period is 2 pi over 968. That's roughly 6 over 968. That's roughly like 1 over 150 or something. 1/150th of a second. So it's oscillating very quickly. And we find that we have an underdamped system, right? We have complex eigenvalues with a negative real part. It's a spiral sink. It's an underdamped system. We do have this oscillation, and we know the long-term behavior already. We knew that as soon as we found our eigenvalues. But if we wanted the general solution to this non-homogeneous system, to this forced harmonic oscillator, well, we did the first part. Now we need to find a particular solution. Ready? Okay. Then our particular solution, we're going to guess, is equal to some constant. What was our right-hand side again? What was V sub s? V sub s, our right-hand side, it said it somewhere, 2e to the negative t over 3. All right. This right here was 2e to the negative t over 3. So we have another exponential function. We know what our guess is going to look like. It's going to look like some constant times, we don't need to add the 2 again, e to the negative t over 3. And now we just plug in, find out what the left-hand side is going to look like, find out what the right-hand side is going to look like, and we're going to be good to go. We know we're not going to have to do any second guessing because negative t over 3 doesn't match any of these. And these were originally from a complex eigenvalue anyway. So we are totally good to go. Not going to have to do second guessing. So what does that look like? What that looks like is, let's look at the left-hand side. Let's look at the right-hand side. And we will do so on the next page. The left-hand side of this equation is LC times the derivative. And again, remembering that our particular solution guess was a e to the negative t over 3. So it's going to be LC times the second derivative of that, which is positive 1/9 a e to the negative t over 3. Plus RC times the first derivative, which was negative 1/3 a e to the negative t over 3. Plus our guess, which is like so. And what you see is that we can actually factor some things out. We can factor out an e to the negative t over 3, and we're left with 1/9 LC times a minus 1/3 RC times a plus 1a. And we can actually factor out the a as well. In fact, let's do so right now. Let's pull the a out. This is now a 1. Let's pull the a out on the right-hand side. You could pull it out to either side. It doesn't matter. Okay? So what is a? Well, the left-hand side needs to equal the right-hand side. The right-hand side was e to the negative t over 3 times 2. So this whole mess needs to equal 2, which is kind of funny. All right. So what do we have? Let's use a calculator. Let's see what the left-hand side is. 1/9 times LC. Again, I'll make it so you can see what I'm typing in. Times LC minus 1/3 RC plus 1. Interesting. This is about equal to 1. So this times a needs to equal 2. So if this times a needs to equal 2, let's call this mumbo jumbo. I don't know. We'll call it snowman. Snowman times a equals 2. How do we solve for snowman? Or sorry, how do we solve for a? A will be 2 divided by snowman, which is approximately 2 divided by this. This is our snowman. I'm actually going to multiply it by, raise it to an exponent of -1. So a is about 2. If you want to be more precise, you could say it's about 2.0007. Yeah, a is about 2. So we have our solution. Our solution is going to be our general solution, which we found to be K1 e to the negative 1250t times cosine. Where did it go? I don't want to switch back. times sine of 968t plus K2 e to the negative 1250t times cosine of 968t plus our particular solution, which was just 2.0007 times e to the negative t over 3. So something very interesting happens here. This is modeling the voltage across our capacitor. We have an input voltage that goes like this. And we're curious about what is the voltage that goes across the capacitor over time. And if you knew much about electric circuit theory, which is more than I do, you'd know that that voltage across the capacitor satisfies this differential equation. And what we said, right, is that these are oscillating. This was kind of like an underdamped harmonic oscillator. They're decaying so fast. And we know that the long-term behavior is going to be that forced response. The natural response decays quite quickly. All general solutions, I don't care what your initial condition is. I do not care what your initial condition is. I don't care about how much electricity you had in the system. Very quickly, the electricity, the voltage going across the capacitor is just going to be the input voltage, basically. Right? This is just that. And I would say that, honestly, we should have been paying more attention to our sig figs. Right? It's probably just supposed to be actually 2. But we rounded earlier, remember? We rounded for this 968. So this is probably supposed to be exactly 2. But I didn't pay attention to my sig figs. Don't tell my physics professor. Don't tell our physics professor. Okay. So let's see what that looks like. That's our general solution. Let's plot this. So it's going to look similar to this. Well, I don't know. Let's just retype it all. Y equals K1 e to the negative 1250t times sine of 968t plus K2 e to the negative 1250t cosine of 968t plus 2 e to the negative t over 3. All right, something very interesting is happening here. I've never seen Desmos do this. Do you know what's happening? Do you know what's happening? Here, let's make it really unhappy. No, we're going to crash the program. What's happening, right, is I told you this decays so fast. And we're oscillating. So our oscillating point is decaying so fast. That's for positive time. You do not want to look back in time right here. If you try to look back in time, this is blowing up so quickly and oscillating. So Desmos is saying it's oscillating so fast that it's getting so big, we're just going to draw a blue block. So let's not look at that. Let's go over to settings here and say let's only look at positive time. Okay. We're only going to look at positive time, and we let's actually put our steady state solution over here too. All right, 2e to the negative t over 3 is what we should be approaching. And we're not quite able to see something. Let's change our axes. Y is going to look from 0 to 2. Excellent. Next, let's start from 0 to 12. And then for different values of k, ooh, wait a minute. I don't actually know what's happening here. Okay, I fixed it. Because there wasn't really much that needed fixing. Desmos was graphing our function. Because if I click on this, we're at the input voltage, right? That's the point. Remember how I said that this part decays so fast that we're basically just the input voltage? Well, yeah, you can see it right here. And if we zoom in a lot, and again, I should really change this so I can see the settings wheel without having to hide things from you. If we zoom in a lot, let's say X is now going from 0 to 0.004. That was Y. Nice try, Jason. 0.04. Y will go from 0 to 2. Then what we can see is we are very quickly decaying. Again, it doesn't matter what K is. Doesn't matter what K is. We are very quickly approaching that green line. Doesn't matter what K is. We're approaching the green curve. And when we zoomed out, this green curve was not flat, right? This green curve was exponential decay. But because we're on such a small time scale, it looks flat. Right? If you zoom in enough, anything looks flat unless it's a vertical line. Or if you zoom in enough horizontally only, anything looks flat. Okay, so that's kind of cool. No matter what the initial conditions were for this system, it's very quickly going into that green curve. And again, we could see that more clearly by, let's look at longer time. Right? You can see again, slightly a longer time scale. It's getting really, really close to that, or even a longer time scale. Currently, this is 6/100ths of a second. Here's 6/10ths of a second. It's already looking like this. And then again, if we actually look at 6 seconds, you can see that exponential decay. And it's just matching perfectly because again, the oscillating component decays so fast. That's what's happening, and that is how we can see an example of everything we've talked about with electric circuit theory, and that's pretty fun. Hope you enjoyed it. That's it for this whole section. Next section, we will get into more fun stuff related to forced harmonic oscillators, eventually building up to the topic of resonance, which is exciting. Bye-bye.